In this video, we're going to talk about something known as kinetic molecular theory, which you'll find is actually probably how you already view the world. And it has so much data behind it that you probably don't even think about it as a theory. It's probably something that you just view as how the world works. But we're going to rewind a little bit and think about how chemistry was developed. Because even though we know all about the periodic table of elements and about atoms and molecules and how they bond, that wasn't how chemistry first got developed. When chemistry first got developed, they could only measure large scale or macro variables, things like pressure. And there's many ways that you can measure pressure, but pressure is really just force per area. Very easy to measure, even if you know nothing about atoms or molecules. You could measure things like volume. It's pretty clear what the volume of a container is going to be. Chemists have known for some time how to measure temperature. They've also known how to measure quantity, or how much of something there is inside of a container. So quantity. And so early chemists thought about the relationship between pressure, volume, temperature, and quantity, especially of gases. And gases are interesting because the volume can change, the pressure changes. Temperature for a solid or liquid can change, but the temperature for a gas, that could affect the pressure or the volume. And you could fit different quantities of it in the same volume. In theory, you could do that with other states of matter, depending on how you do it and the molecules you're dealing with, but it was most obvious with gases. And based on these macro measures, chemists were able to come up with some generalizations. They were able to come up with what we now call the ideal gas law, that pressure times volume is going to be proportional to, and they use R, the ideal gas constant, for proportionality. It's going to be proportional to the amount of the gas we have, and we measure that in terms of moles, but that's really just a quantity of gas, and then times the temperature. Once again, all of these are macro variables that chemists have known how to measure well before we had any substantive proof that things like atoms and molecules existed. And chemists understood how these things related. As we just talked about, chemists saw that if you were to say hold the amount of the gas constant, and let's say you were to hold the volume constant, if you were to increase the temperature, that would then increase the pressure. They weren't necessarily exactly sure why this was happening, but they saw that this in fact did happen. And instead of holding the volume constant, if you allowed the pressure to be constant, but you allowed the volume to vary, and you were to increase the temperature. So this would be a situation where you are increasing the temperature inside of a balloon. Then the volume would increase. And if you held temperature constant, and you increase the number of molecules, and you hold pressure constant, volume would increase. If you hold volume constant, temperature constant, and you increase the number of molecules, then pressure would increase. And so those were all of the clues that were used to come up with this relationship that pressure times volume is equal to or is proportional to the quantity of the gas you have times the temperature. But then chemists said, well, this is nice, but what actually is going on? What actually are gases? And this is where the kinetic molecular theory comes into play. Early chemists said, hey, maybe gases are a bunch of particles in constant random motion. So let me make a container here. And they said, we're going to have a theory. And we're going to say, and a good theory is one that would explain the phenomena that you are observing. And says, well, what if gases are nothing but a bunch of particles here that are in constant random motion? Here they are, they're moving around, constant random motion, that the volume of the individual particles is a very, very small part of the broader container, and that these particles, for the most part, are not interacting with each other. And so you're imagining this theory, this mental model, where you have a bunch of these things, they're so sparse that they're not really interacting with each other, and they don't have these intermolecular forces. Of course, later we'll learn that that isn't exactly right, but for approximation, if we assume that, and that they're having perfectly elastic collisions with the side of the container. And it's these collisions, and these perfectly elastic, which means no loss of kinetic energy, that's what's generating the pressure. Because if you have enough of these particles bouncing off, you're going to have a force per unit area on the side of this container, and you could measure that in terms of pressure. And then to say, well, if you're to hold the amount of the gases constant, why does increasing the temperature increase either the pressure or the volume? Well, what if temperature is really just a measure of average kinetic energy of these particles? That if you increase the temperature, then on average, these particles have higher kinetic energy. They are vibrating more, bouncing around with even more energy. And then that obviously, if you hold volume constant, would increase the pressure. Or if you kept pressure constant, in order to keep pressure constant, you would have to have a larger volume so that the force per area stays the same. Now, what's interesting about this particulate model, this kinetic molecular theory, is that it has stood the test of time. And it is completely consistent with everything we know now about atoms and how they bond and molecules and states of matter. We now take this for granted. In fact, when I first learned this, I was just like, well, isn't this somewhat obvious? Until I realized this was not how chemistry originally developed. Chemistry originally developed by people measuring pressure, volume, some form of quantity and temperature, figuring out how they relate, and then saying, why do gases behave that way? Maybe a gas in a container is a bunch of these randomly moving, constant motion particles bouncing off the side of the container, and that's what's providing the pressure. And the temperature is the average kinetic energy of those particles. And as you'll see, the rest of our chemistry careers, we're going to be just building more and more on this kinetic molecular theory, because it is, as far as approximations go, it is accurate. We'll see that it's really describing closer to what you could call ideal gases. The real world has a little bit more imperfections in it. You actually do have interaction between particles. The particles themselves have some volume associated with it, although it's a reasonable approximation that relative to a lot of containers, it might be negligible.